Yeah, so we do what's in the parentheses first. We've got our fraction bar here, which tells us we have to work on top of that fraction first. So another enclosing symbol. Well, then there's another parentheses up there. So we have to do this piece here first. So what is 10 to the 5th divided by 10 to the negative 4? 10 to the 9th. 5 minus negative 4 is 5 plus 4, or 9. Now, the next thing we would need to do up there is the 10 to the 9th squared, which is 10 to the 18th. And then finally, we got the 10 to the 18th times 10 to the negative 7, which is 10 to the 11th. So that's what we get on top, 10 to the 11th. On bottom, we've got another set of parentheses here. What is 10 to the 6th times 10 to the negative 11th? 6 plus negative 11 be negative 5. Now we have to do that power. 10 to the negative 5th to the power of negative 4. 10 to the 20. Now we've got an extra step on this one. We have the 10 to the 3rd divided by 10 to the 11th. 3 minus 11, negative 8. Then 10 to the negative 8 times 10 to the 20th, 10 to the 12th. So now at this point, we're dividing 10 to the 11th divided by 10 to the 12th. 10 to the negative 1 to the power of negative 3. Well, it's negative 1 times negative 3, which is 3. Very good. I would not be quite that cruel to you on a quiz or a test, but I would expect you to be able to do something like this. So doing something like that, you do the top first. What's 10 to the 6th times 10 to the negative 15th? Negative 9. 6 plus negative 15, negative 9. You had the right idea. I knew what you were thinking. So then down here, 10 to the 7th, 10 to the negative 7th times 10 to the 4th. 10 to the negative 3rd, right? Negative 7 plus 4. When we're multiplying with like bases, we add the powers. So then we got 10 to the negative 9th divided by 10 to the negative 3rd. We're dividing, so we subtract. So that's negative 9 minus negative 3, which is negative 6. Then that's still to the power of negative 4, which is going to give us negative 6 times negative 4 is positive 24, 10 to the 24th. Any questions? No? Okay, perfect. So we left off yesterday talking about scientific notation. So let's take a peek at those conversions first of all. What is this going to become in scientific notation? It's 2.4, right? Times 10 to the negative 8. Yeah. The decimal point had to move 8 spots. So that's where the 8 comes from. And this is a really small number, so that means it's in those negative power of 10 place values. It's negative 8. 10 to the negative 8. How about this one? to the 11th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's 10 to the 11th, and what goes in front of it? 7.3. Okay. Well, now that we have that, let's take a look at calculating with it. Remember, when we add or subtract, one, we need the same name. For fractions, that was common denominators. For whole numbers, it was the same unit or even the same place value. That's where we lined up the columns to add and subtract. And then we combine the counts, but once we combine the counts, we keep the same name. So again, in fractions, that was keeping the common denominator. In whole numbers, it's keeping the same unit. Inches plus inches stays inches, and so on. In our whole numbers, the name came down to the place value. So if I have a number like 7.3 times 10 to the 8th, what part of that number indicates a place value? 10 to the 8th. 10 to the 8th is the 100 millionth place. So in order to add numbers in scientific notation, they must have the same power of 10. Now I'm putting parentheses around these not because there's anything I need to do there. Just like with the negatives, it's just separating it to indicate that is a single number. So here we have the same power of 10. So they have the same name. We can add them. And when we add, we combine the counts. So this is the counts. What is 7.3 plus 2.1? 9.4. And we keep the same name, 10 to the 8th. Bless you. Do these have the same name? Yes, they do. So we're going to combine the counts. 4.2 plus 8.5. It's 12.7 times 10 to the 11th. Are we done there? Well, since I haven't asked it before and I'm asking on this one, that's probably an indication that we're not, right? What's wrong with this? We have 2 digits in front of the decimal point. Proper scientific notation only allows 1 non-zero digit in front of the decimal point. So I have to move it. Yes, we have to change our power of 10. The key is our number got smaller or larger. Smaller. It went from 12 down to 1, right? The number got smaller, the power has to get larger. So the number got smaller by 1 place value, power gets larger by 1, so it is 10 to the 12th. So these have the same name, so we can go ahead and add them. What do we get here? Combining the counts, 8.1 plus 6.4. 14.5 times 10 to the negative 8. Of course, we're not done. We're going to move that decimal, 1.45. Yes, we have to add 1. Negative 8 plus 1 is a negative 7. Be careful of those negative powers. A lot of people mess that one up. Bad guy. Good thing. That's true. The negatives, if you're 1 less, is, yeah. Makes sense. Okay, so what if we have something like this? where we don't have the same name. But we're going to have to change one of them to make them the same name. Usually, if we're adding, we're just going to change it to the larger place value, larger power of 10. So we're going to change them to the 10 to the 9th. So this is going to stay 7.23 times 10 to the 9th. This one is going to become 10 to the 9th. Now the power of 10 got bigger, so the number has to get smaller by a decimal place. So now we can add 7.23 plus 0.94 is 8.17 times 10 to the 9th. What do you think? You're reading my mind. I was actually starting to write it already when she said it. So you can't totally blame her for it. I always make it worse. It's my job. So now here, we've got negative 3.8 times 10 to the 9th plus 5.4 times 10 to the 9th. We do have the same power of 10, so we can combine them. What is negative 3.8 plus 5.4? $1.6, right? Times 10 to the 9th. So that's not even so bad. Subtraction follows the same rules. Hang in there. So 5.3 times 10 to the negative 12th minus 2.7 times 10 to the negative 12th. They have the same name, same power of 10. So just combine them with 5.3 minus 2.7. It's 2.6 times 10 to the negative 12th. The only thing can get tricky at all with our subtraction is we might have things like this. 7.28 times 10 to the 7th minus 6.83 times 10 to the 7th. They have the same power of 10. So we'll go ahead and subtract. 7.82 minus 6.83 is 0.45. And we keep that same name, times 10 to the 7th. What is wrong with that? Yeah, there's no digit in front of the decimal point other than zeros. We've got to move that one spot to make it 4.5. Now this time the number got larger. It went from 0.4 up to 4. So the power needs to get smaller by 1. 7 minus 1 is 6, 10 to the 6th. So if we have 5.37 times 10 to the negative 9 minus 4.91 times 10 to the negative 9. Do they have the same name? Yep. So let's subtract 5.37 minus 4.91. 0.46, right? Times 10 to the negative 9. What do we got to do with that? Same thing. Move the decimal point over, 4.6. This becomes, yes, negative 9 minus 1 is negative 10. Not so bad? Beautiful. When we multiply or divide, if you remember, we do not need the same name. So in fractions, that was when we didn't need the common denominator. We didn't have to have the same units. We combine our counts, but we also combine the names. So let's take a peek. We can have 7.2 times 10 to the 8th times 3.4 times 10 to the 13th. We don't have the same name and it doesn't matter. We're going to multiply the count. 7.2 times 3.4. $24.48 times, now we also combine the names, 10 to the 8th times 10 to the 13th. We're multiplying, we add powers, right? 8 plus 13 is 21. But we're not done yet. We've got 2 digits in front of the decimal point, so we've got to move it over. 2.448 times, does this get smaller or larger? Larger, 10 to the 22nd. The number got smaller, went from 24 down to 2, so the power gets larger. So something like this, 3.5 times 10 to the 11th times 2.1 times 10 to the negative 8. Multiply the counts. 3.5 times 2.1 is what, 7.35? Times 10 to the 11th times 10 to the negative 8th. To the third, you got it. We're multiplying, so we add powers. 11 plus negative 8 is 3. And that's it right there. Nothing to adjust on that one. $8.4 times 10 to the negative 12th times 6.1 times 10 to the negative 9th. So 8.4 times 6.1 gives us 51.24. Times 10 to the negative 12th times 10 to the negative 9th is 10 to the negative 21. Then what? Because when we're multiplying, we add the powers. So that's just going to be negative 12 plus a negative 9. So we move that decimal point, so it's 5.124. Does the power get bigger or smaller? Bigger. Number got smaller, went from 51 down to 5. Power gets bigger. Negative 21 plus 1 is negative 20. What if we have something like this? 7.35 times 10 to the 12th divided by 3.5 times 10 to the 19th. We divide the numbers. 7.35 divided by 3.5 is 2.1. Times, we also then divide the names. 10 to the 12th divided by 10 to the 19th is 10 to the 12 minus 19 is negative 7. Good. So we might have 6.76 times 10 to the negative 7 divided by, this makes more sense if I do 5.2 times 10 to the 11th. So 6.76 divided by 5.2 is 1.3 times 10 to the negative 18. Really, very good. Let's do 5.76 times 10 to the negative 6 divided by 9.6 times 10 to the negative 11th. So what is 5.76 divided by 9.6? 0.6 times 10 to the, what's negative 6 minus negative 11? Comes out to be a positive 5. You are correct. Are we done? No. Move that decimal. This becomes 6 times 10 to the 4th. Very good. The number got larger, so the power gets smaller. 5 minus 1 is 4. We can even play around a little bit with powers. Like this one, 1.2 times 10 to the 8th to the 3rd power. What's 1.2 to the 3rd power? $1.728. And then we also do the name to that power. 10 to the 8th, the power of 3 is 10 to the 24th. 8 times 3 is 24. Look familiar? Good enough. Oh, let's see. Yeah, we'll call that good enough for those. I want to talk a little bit about the engineering notation. We mentioned it yesterday, said we would get back to it. Engineering notation was a great idea. It gets used a lot, but not kind of in the form that it was intended. Engineering notation is a lot like scientific notation, only it limits the powers of 10 to multiples of 3. So what that means is they can be 0, 3, 6, 9, 12, negative 3, negative 6, negative 9. But that means then, of course, then in front of the decimal point, there can be 1 to 3 digits before the decimal, instead of just 1 digit in front of the decimal point. So let's take a peek at that. If I want to convert this into engineering notation, I can go 1, 2, 3 spots. Can I go 3 more? Sure can. 4, 5, 6. Can I go 3 more? No. So that is 620 times 10 to the 6th. On this one, I can go 3 spots. 1, 2, 3. Can I go 3 more? Well, it kind of looks like I can't, but I have to because right now there's nothing in front of the decimal. So 1, 2, 3, 4, 5, 6, I should say. So that's 59 times 10 to the negative 6. The really tricky ones might look like this. I move my decimal point 1, 2, 3 spots. Can I go 3 more? Again, it looks like there's not enough digits there, but right now there's no non-zero digits in front of the decimal point. So I have to go 3 more. So 4, 5, 6. I've got to add a 0 there. So that is 270 times 10 to the negative 6. So here, I move the decimal point. 1, 2, 3. Can I keep going? 4, 5, 6. Keep going. 7, 8, 9. Keep going. No. So that's 32 times 10 to the 9th. Why would we complicate scientific notation with something like this? Well, because since you guys are automotive, you do a lot with electronics, it's our metric prefixes. You guys deal with volts and millivolts, microvolts, kilovolts, megavolts. All look familiar? And it might be mega ohms rather than megavolts. Megavolt is pretty large, but megawatts for power, kilowatts. Each of those is a power of 10. Milli is 10 to the negative 3. If you think of the regular unit as being 10 to the 0, milli is 10 to the negative 3. Micro is a millionth, or 10 to the negative 6. Kilo is a thousandth, or 10 to the 3rd. Mega is a million, or 10 to the 6th. So if I am doing operations with metric numbers, V equals IR, of course, is your common Ohm's law. Have you guys got that far in DC electric yet? Okay. So let's say you have a current of 24 milliamps and a resistance of 800 kilo ohms. So this is going to be 2.4 or 24, milliamps times 800 kilo ohms. The 2.4 milliamps is actually going to be written out as 2.4. 24 milliamps. It'll be 24 times 10. Milli is negative third amps. 800 kilo ohms are going to be 800. Kilo is 10 to the positive third ohms. We multiply that out. 24 times 800 is 19,200, right? 10 to the negative 3 times 10 to the positive 3 is 10 to the 0, right? Negative 3 plus 3 is 0. Amps times an ohms is a volt. Now, of course, we should adjust this to 19.2. Decimal point just moved 3 spots. So this gets larger by 3 times 10 to the 3rd volts. 10 to the 3rd means what? Yes, 10 to the 3rd means kilo. So that's 19.2 kilovolts. That's a lot of volts, yes. It's not the volts that hurt you, it's the amps. It takes less than 0.2 milliamps to stop your heart. Stop the human heart. You have to get it to the right place in the body for it to do the damage. Yeah. So in your book, page 130, exercise 2.6. 59 through 81. It's finishing up what we started yesterday. And then on page 133, exercise 2.7, 1 through 23, the odd.